None of these problems are a problem to me. This is 714, best time to buy and sell a stock with transaction fee. Okay, so you're given an array prices, where price is I is the price of a given stock on the ith day. Okay, so it's just some array. It has, I guess, integer values, and that integer value is the price of that stock at that corresponding day. So, in this example, the price of the stock on day 0 was 1. The price of the stock on day 1 is 3. The price of the stock on day 2 is 2, 8, 4, 9, etc. And you're also given an integer fee representing a transaction fee. So a transaction fee is just the amount of money you have to pay once you complete a transaction where you buy and sell a stock. So maybe you buy the stock at price $3, right? You buy a $3 stock, you sell it at $6. You just made a $3 profit off that transaction, right? If you buy it at 3, you sell it at 6, 6 minus 3 is 3, you made $3. But say the transaction fee was $2, well, that means you have to pay that transaction fee. So in total, you netted $1, right? You bought at 3, you sold at 6, you paid the $2 transaction fee. 6 minus 3 minus 2 is 1. So you made $1 on that transaction due to the transaction fee. So the thing about this problem that you think about is, well, if we're trying to find the maximum, which we are, you can't just keep doing as many greedy transactions as possible, because every time you do a transaction, you have to spend that fee. Okay, so find the maximum profit you can achieve, right? So if you want to find the maximum profit, you have to think about when you're buying and how many times you should buy, because every time you buy and sell, you have to pay that transaction fee. You may complete as many transactions as you like. Again, you may as many as you like, but the more you do, the more of that fee you're going to have to pay. But you need to pay the transaction fee for each transaction, right? So it's not just a one-time thing. You don't pay it on one transaction and that's it. No, you pay it on every single transaction you do. Every time you buy and then you sell, you pay that transaction fee. Note, you may not engage in multiple transactions simultaneously. You must sell the stock before you buy again. Okay, so that basically means you can only hold on to one share, right? You can only have one share of the stock at a time, because when you buy the stock, you have the stock. You can't buy it again. You can't buy multiple shares. You're either holding the stock or you're not holding the stock. So you buy the stock and then you can sell it. You can't buy the stock and then buy another one. And likewise, the other side of that coin is you can't sell the stock if you don't own it, right? There's no short selling margins or whatever. I'm not that involved in, the stock market and equity markets and economics. I just like the Leetcode, so I don't really know how that works. But you can't sell something if you haven't bought it already, right? So, you have to sell it before you buy again, right? And you have to buy it before you sell it. So those are kind of flip sides, two sides of the same coin. All right, so with all that said, let's go ahead and get into the example problem and see if it makes sense. So we're given prices equals, we have prices equals 1, 3, 2, 8, 4, 9. And we have this fee of $2. Or 2 units of money, whatever that is to you, whatever that means to you. 2 euros, $2, 2 rubles, 2 yen, 2 pesos, whatever. I don't know. But that's the price. So the optimal solution apparently is buying here at 1, right? So we buy our share here, and then we sell it at 8. We buy it again at 4, and then we sell it at 9. Okay? Now, what's the total amount of money that we get from that? Well, when we're buying the stock, we're going to go underwater $1, right? If you wanted to think of it in this terms, maybe it'll help you a little bit with the problem, right? When I buy the stock here, I lose $1, right? And what I'm going to say is, well, I lose $1, and I know that I'm going to have to pay a transaction fee when I sell it. So I'm going to just account for that early, right? So I lose $1 for buying it, and then I lose another $2 because I have to pay this fee. So I had to spend $1 to buy it, and then I have to spend $2 to pay this fee. And then when I sell it at 8, Right, so maybe the colors of this should be different. Right, when I buy it, I lose money. Right, red is always bad and green is always good, whatever. I don't know where that comes from, but it's a weird psychological thing, you know. Red's a bad color, green's a good color. Green means you get to go. Red means you have to stop. Right? Red stock means it's declining in price. Green stock means that it's increasing in price. Decreasing in price to increasing in price. Words. Okay. So then when we sell at 8, we're going to just make $8, right? And then when we buy at 4 again, well, we have to spend $4 to buy this freaking stock. And then, because that's the price of the stock, and then we also have to pay that transaction fee again of -2. Right? I could put the -2 over here or over here, right? I could account for the fee when I buy it, or I could account for the fee when I sell it. It doesn't really matter, right? The fact is that when I do a transaction, which is a buy and then a sell, I have to pay that $2 fee. And it may not be clear in the problem, right? Because it just says that there's a transaction fee, but if you don't do the example, right? I know this because I've already looked at the example. You may think, oh, do I have to pay a transaction fee when I buy and when I sell, right? But it doesn't really make that clear, or does it? It just says for transaction. So it just happens once per the buy and sell process, right? You don't have to pay it when you buy and then pay it again when you sell it. You just have to pay it when you complete a transaction, which is both buying and selling, you know, those corresponding parts. Okay, and then finally, just to finish this problem, when I sell at 9, I make $9. So what's the total of this system? Well, you know, I lose $1, I lose $2, I lose $4, I lose $2, and I gain $8 and I gain $9. So in total, that is what? So this is equal to 8, right? Because, you know, 4 minus 2 is -6, minus 2 is -8, plus 8 is 0, plus 9 is 9, minus 1 is 8. Shows you a weird way that I do math sometimes. Okay, but the total you get is 8, and that's why the output here is 8, right? So, you know, you account for the fact that you lose $1, right? So you think about how much money you have, right? If you thought about how much total money you have, well, you just lost $3 doing this. You gain $8 back. You lose another $6 doing this, and you gain $9 back. Now, something to note in this problem, right? The way that it's stated is that you never see 2 reds in a row, right? You never see 2 greens in a row. Why? Because what does that correspond to? Well, green corresponds to selling, right? So you can't have 2 greens in a row because you can't sell twice in a row, right? You can't sell twice in a row because that would mean that you sold the stock and you sold it again. Well, you can't sell it until you buy it, right? And you can't buy it again until you sell it, if that makes sense, right? There can't be 2 reds in a row because that would mean that I bought it twice. I can't buy it twice. I can only buy it once, right? I have to hold it, and then I have to sell it, and then I have to sell it before I can hold it again, right? So if I wanted to think of this as a graph, so let's go ahead and do that for this particular problem, and then maybe we can generalize the argument from it, right? Because there's this idea of like buying and selling, and the fact is that I can't sell unless I've already bought, and I can't buy again until I sell. So that might help us think about states and how we can model this problem as a dynamic programming solution, where the graph is a directed acyclic graph, which is a candidate for dynamic programming, blah, 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 blah. Let's go ahead and just model this as a graph and think about what we can do to make this more simple. So the observation that we're going to think about mostly when we solve this is this note, right? Which is, you may not engage in multiple transactions simultaneously. You must sell the stock before you buy again, right? And you see that in this problem here, right? You can't have 2 reds in a row. You can't have 2 greens in a row because you can't buy then buy. You have to buy then sell. You have to sell before you buy again. Right, so that's really the observation which is going to help us here. But anyways, let's go ahead and write this before I ramble too much. So let's draw this graph. Okay. So I'm just giving each day its own node, and then the price on that day as the value of the node. 8, a 4, a 9. Okay, so this is where the biggest leap of faith has to come. So I need to think about how I'm going to describe this so it's not confusing. Well, you know, if we said that green edge was selling the stock, right? If I sold the stock in this position, I'd get plus $3, right? If I sold the stock at this position, I get plus $2, right? Because the stock is what I'm holding. So if I sell it going into 2, that means I sold it on this day, so I get $2. If I sell it at 8, I get $8, right? If I sell it at 4, I get $4. And if I sell it at 9, I get $9. That makes sense, right? If I sell the stock on day 1, right? This is day 0. If I sell the stock on day 1, I get $3. If I sell the stock on this day, I get $8. Okay? And if you thought about the edges of buying the stock, where if I bought the stock on day 1, I'd lose $1 and I'd lose the fee. So let's just say that fee equals -2, or fee equals 2. So I don't have to write minus fee. Just know that when I do -2 here, right? So we'll, how are we gonna do this? So I'll just put -3 here. So this is basically saying, you know, I lose -3 if I buy on this day. Why? Because I lose 1 for buying the stock and I lose 2 for spending the fee. If I buy the stock here, I'm gonna lose -3 for buying the stock and -2 for paying the fee. I'll lose -2 for buying the stock and -2 for paying the fee. I'll lose 8 for buying the stock, and then I'll lose 2 for paying the fee. I'll lose 4 for buying the stock, and I'll lose 2 for paying the fee. I'll lose 9 for buying the stock, and I'll lose 2 for paying the fee. So this is the system of edges, right? Where the red edge, the nodes, right? The nodes are the, what are the nodes? The nodes are the nodes. The nodes are the days. The value of the nodes, right? These 1s, these 3s, that's the price of the stock on the day. And then the edges, right? The red edges are the edge you would take if you're going to buy the stock and the total cost associated, right? And the green edges are the edges you take if you want to sell the stock, and the value is the amount of money that you would get, right? So the red edges are saying, okay, if I take the red edge, right? If I take the red edge in this system, I'm saying, okay, I want to buy this stock, and here's the fee that I'm going to have to pay. And if I take the green edge, that means I'm going to sell the stock, and that's the price that I'm going to get, right? I'm going to get $2 for it. And it'll just capture the delta, right? Because I get $2 total, but I've already accounted for the fact that I've already bought the stock. And so at the end, we just say, okay, on the last day, what's the total amount of money that we can get? So this is the basic idea of the problem, right? There's edges corresponding to buying. There's edges corresponding to selling. This is a DAG. Everything's good. We just need to find the maximum path in this DAG, and that will correspond to the maximum profit that we could get, right? Well, sort of, right? The issue is with the way that this DAG is stated, the way that we model this problem. If we try to find the maximum path, what would that be? Well, the maximum path would just be like, okay, if I start here, for example, or maybe I start here. I buy the stock, I sell it. What's the maximum path going to be from here? Oh, I'll sell it again. 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 Right? That's all right. I mean, if we found the maximum path in this graph, that's what it would be, right? Well, sounds good to me, right? I just kept selling it. Sell, sell, sell. That's like every day I'm selling and selling and selling. Why doesn't this work? Well, because I can't sell again unless I buy again. So this graph needs to kind of be decoupled, right? I have all the right information, but the way that it's stated, if I ran dynamic programming to find the maximum path in this graph, it would just keep saying sell, 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 sell. So we need to create a state, right? We need to create a state that says, okay, if you're in this state, that means that you sold. And if you sold, you have to buy before you can sell again, right? Because the problem here is I sold, but then I buy, but then I sold. But if I'm in this state where I've sold, I shouldn't have the option to sell again, right? So I need to decouple this system. So in order to do that, what we will do instead is we will copy this graph and we'll create a duplicate where we think about the fact as to whether we have sold or bought. Meaning that if I'm going to think about, well, we'll create two states. So we'll call this top state. I am not holding the stock. And this bottom state will be I am holding the stock. Okay. So I have a top state where I'm not holding the stock, and I have a bottom state where I am holding the stock. So what that basically means is, instead, let's, well, I kind of want to keep stuff, but then I don't want to keep stuff. Okay, let's just erase it, whatever. So, essentially, if these bottom nodes and these top nodes represent whether we are holding the stock or not holding the stock correspondingly, what would these red and green edges look like in that case? So we'll deal with the first node separately. So when you start the day, right, when you're in the very beginning, what can you do? Well, in order to hold the stock, you have to buy it, right? If I'm holding the stock or these bottom nodes, that means you have to buy the stock. And that's going to have a fee of 2 and a cost of 1 for the stock itself. So that's going to put you -3 in the hole. Or you can just decide that you don't want to hold the stock and you just want to do something neutral and just stay in the same situation you were before. Okay. Now the next day, well, from here, right, from this state, either I can buy the stock, and that'll have cost of -3 for the stock itself, and then price 3 for the stock itself, and price 2 for the fee. So that'll put you -5 in the hole. Or you can stay neutral and do nothing. From this state, well, I'm now holding the stock. So if I'm holding the stock, I can sell the stock and take in those tendies, right, those gains, and that'll give me 3. Right, if I sell the stock when I'm holding it, I can get 3. Or I can decide, you know what? I'm just going to keep holding the stock because I think things are going to get better. When I'm at 3, well, I'm not holding the stock. So either I can continue to decide to not hold the stock. Right, at any node, I can continue to decide to be in the same state. So just to kind of speed up this whole process a little bit. Right, in any state, I can decide that I don't want to change where I'm at. I want to keep holding or keep not holding, I guess. So at 3, right, since I'm not holding the stock, I can I can buy the stock. Right, if I buy the stock, it's going to put me -4 in the hole. Right, at 2, this is going to put me -10 in the hole. This is going to put me -6 in the hole. And this is going to put me -11 in the hole. Right, because each time I buy the stock, right, if I'm not holding in order to buy it, I'm going to have to spend this much, right? And then on the other side, if I sell the stock, right, here I'll get 2. Here I'll get 8. Here I'll get 4. And here I'll get 5. So is this system better encapsulate the idea, right? Because before what would happen is I could just keep selling, right? But now that we've separated the system, we've decoupled it into states where I am holding and I'm not holding. You'll notice that once I sell, right? Once I sell something, I have no choice but to buy again before I can sell again. I don't have any green nodes from travel. I don't have any green edges traveling out of these nodes because I'm not holding any stock, right? So as soon as I buy a stock, then I have the freedom to decide when I sell again, right? And similarly, the other side of that coin is, you know, I can't keep buying a stock, right, until what? I just had a total brain fart. So if I sell the stock, buy the stock, sell the stock, buy the stock, you see what I'm saying, right? In this problem, I have to sell the stock before I sell it again, right? Because once I sell the stock, there's no green nodes until I buy again. And I can't buy twice, right? In order to buy again, right? Because when I buy, I go negative. In order to hold the stock again, I have to sell it before I can hold it again, right? There's no red edges leaving these nodes at the bottom, and there's no green edges leaving these nodes at the top. I'm kind of exhausted that point, but hopefully that makes a little sense. It is kind of complicated, this graph. So now if we run the graph of finding the max path, right? Well, the max path up to this node is just 0 itself, right? And it'll have value 0 because we're talking about the values of these edges. So how are we going to do this? Let's do purple or some other color because there's too much going on. So the value here is 0. It's too dark purple. This purple is not good. It's a bad purple. Okay. 0 itself here. The value here is -3, right? Because the only option it has is this node. Okay, and then we can look at this next node here. Right, going to this node, I can take 0 or I can take 3 and 3. So I can either go -3 and get 3 and get 0 or 0 again. So either way, it's going to give me 0. Right, from this node, I can take -3 and get to -3, or I can take -0 and -5. So the best would be just to stay at -3, right? So So this selected path so far is here. So I'm just trying to think about how I'm going to do this so it's optimal. Here and here, and this node took here and here. Okay, now that we're looking at 2, well, 2 could get 2 plus -3 if it used this link. Right, if it uses this link, it'll get -1. And if it uses this link, it'll get 0. So it's going to choose this link. And it'll have a cost of 0. Okay. At this link, I can choose -3 or -4, right? If I choose this link, this is so confusing. I get -4 because I have 0 total and I get -4, so -4. Or I can choose -3 and 0 and get -3. So it's going to choose this link and still be -3. Okay, at this node, here's where it gets interesting, right? Let's move this up so the weird thing is in the way. So 8, it can get 0 from here, right? I can use this link and get 0, or I can use this link and get 8 plus -3, which is 5. So that's actually the optimal path to get you to 5. Here you get -10 if you buy at this point, or you get -3 if you take this point. All right, so let's just run through this. Boom, boom. So better to stay at -3. At this next node, right, at 4, I can get 5 from this side, right, 5 plus 0. Or I can get 4 plus -3, right, 4 plus -3, which is 1. So I get 1 or 5, so it's better to choose 5. So I'll take this link. This will give me 5 points. At here, I can get -6 if I buy here. or 5 plus, yeah, so I'd have 5 already, plus 6 is -1. Or I could hold on to what I had before and get -3. So it's actually better to choose this -6. All right. Take that path. And that'll give me -1 in total. This should not be a 5. This should be a 9 here, right? Because there's 9's the value that I get if I buy this. So excuse me for that. For some reason I haven't cycling these. Okay, and then now 9. So if 9 uses the 0 path, it gets 5. Right? And if it uses this -1 path, it gets 9 plus -1, which is 8. So it's going to prefer the 8. Right? Setting this to 8. And then here, 5 minus 11, -6. Or here I have -1, so it's going to prefer the -1. All right, so I'm just going through a basic dynamic programming approach where you look at all the edges going into a node to determine what's optimal for that node. All right, so this would be -1. And then you'll notice these blue paths. Well, what's the optimal path here going through the whole system? So there is a path going from here to here, to here, to here, to here, to here, to here. And notice that's the exact path that we would take to get the optimal, which is of value 8, right? We buy on the first day, we hold, we sell at 8, we buy again at 4, and we sell at 9, right? So we buy, hold, sell, buy, sell. And that gets you this optimal value of 8. So that's essentially this problem, right? So in summary, what we had to do is we looked at the price data, we figured out how we can model out a graph, what the edges would look like based on the transaction, realized that there's multiple states, right? There's a state where you're holding the stock and there's a state where you're not holding the stock, because that will determine what you can do at that state. What you can do corresponds to the edges that you would traverse, right? If I'm not holding the stock, then I have the option of either buying or not, or just continue not holding, but I don't have the option to sell because I'm not holding anything, right? And likewise, when I'm holding the stock, I don't have the option to sell the stock again. I only have the option to either, if I am holding the stock, I don't have the option to buy the stock again, right? So there's no red nodes. I only have the option to either sell the stock or continue holding. Okay, so that was decoupling. And then from that, we can solve this problem. So you could do this with linear space. It's obviously linear time, right? Because you just look at each node twice, kind of, because you have to use a state where the node you're holding, at the day you are holding the stock, or at the day you're not holding the stock. But you could also, so it's definitely linear time, sorry. But it could also be constant space, since you're only considering the previous day's value in order to find the current day's value, right? In order to find this node's value, you only had to look at the previous day's information here and the previous day's information here. To find this node's value, you only had to look at the previous day's information here and the previous day's information here. So you don't actually have to keep track of everything, just of what you're holding or buying on a corresponding day. So in order to make that point clear, let's try to find the recurrence relationship. Even though we just walked through a problem, let's try to find what it is exactly for any state. Right, so let's say this is state I. Right, so the dynamic programming solution, when you're holding, if you're holding the stock, okay, I'm not holding the stock, so not holding, sorry. Is what? Well, you have options, right? Either I continue not holding. Whoa. Forgot that I left that big. I continue not holding. So that's just saying, well, I'll just take whatever not holding was at the previous iteration. Or what's my other option? I can sell the stock if I was holding it before. So I can take D of holding right? How much money do I have when I'm holding at the previous state, plus the price of the stock at this state, because that's how much money that I'd get. Right? The amount of money I'd get if I sold at this state is 8, because that's the value of the stock at this day, right? So either, if you wanted to think of it like this, right? So I'll color these states so you know what's going on. So either I do nothing, right, when I'm not holding, which corresponds to this link here, or I sell the stock, which corresponds to this here. Right. Now what about the flip side? What about when you're in this state I here? Right, on day I. Well, similarly, right, so D of holding of I. Well, either, yet again, I do nothing, right? So I continue holding from the previous day, which is this link here, right? Ugh, why can I? It's so weird what I can't do sometimes. Or I decide that I'll go from a previous day where I wasn't holding. So however much money I have at the previous day if I'm not holding, minus the price of this day, because that's the amount of money I'm going to have to spend to buy this stock, minus the fee. Right? Because in order for me to take this 8 length, right, I'm going to have to pay $8. So if I'm not holding, that's how much money I have when I'm not holding. I have $0. And then I'm going to have to pay $8 to buy the stock minus the fee, which is $2, right? So $8 to buy the stock minus the fee plus whatever I had at the previous day in terms of money. I'm not holding here. So these are the two recurrence relationships. Notice since everything, like I said before, is based on the previous day, we can get constant space if we just say, well, we don't need to, since we're only updating I based on I minus 1, we can just keep track of not holding and holding, and that'll get us the solution, right? I can rewrite this. Or I can just say not holding, I'll just call it NH. Not holding equals the max of whatever not holding was before, or whatever holding was plus the price at I. And holding equals the max of whatever holding was before, or not holding minus the price of I minus the fee. Right, and then you'd have to do these at the same time. But notice how it's constant now, right? So we just have these two variables, not holding and holding, and we just update them at each iteration of the loop. So that's pretty much the sum. That's pretty much the summary of this problem. I guess the only exception you need to think about is that there's kind of an edge case, not an edge case, but there's a separate situation for a single state, and that's the first state, right? For this state, you have no option of doing nothing, right? For this first state, right, is different, right? Like for every subsequent state, like this state, I can do nothing or I can buy, right? This state, I can do nothing or I can buy. But notice at this state, the only option I have is buying, right? Because there's nothing, I can't do nothing because there's no previous state where I'm holding the stock, right? Because this is the first day. So on the first day, I'm definitely not holding the stock. So, I mean, I have no option of choosing a previous day where I was holding the stock. And then same here, right? I can't, right? For all these subsequent nodes, I can sell, right? There's a state where I can sell, but here I can't sell, right? Because it's the first day. How am I going to sell if there's nothing? It's the very first day, so I can't sell something because I haven't even had a chance to buy it yet, right? And same thing here. I can't decide to keep holding the stock because I haven't even had a chance to buy it yet. So there's an exception here that we'll account for. But with that, let's go ahead and get right into this problem. Okay, so we'll create the holding and not holding. We'll just call it holding and not holding because that's what we called it in our problem description. So in our recurrence relationship, so might as well just stay consistent, even though it may not be the best naming convention. So you'll notice that when you're not holding, your first price is 0 regardless. And when you're not holding, your price is 0 regardless. And when you're holding, you're going to have to pay that first fee, which is the price of the stock minus the fee. So we'll just say price at 0 minus the fee. Ugh. Okay. And then we'll look at I for each day, I and range length. Well, we don't have to look at the first day. Length of prices, because we've already accounted for the first day here. Right? We've already transacted. We're going to start in this state here. Okay. And then what are we going to do? We'll just update this system using this recurrence relationship. So not holding equals max of not holding, holding plus price of I. Okay. So don't forget that. Not holding equals max of not holding, holding plus price of I. Now we have to do this on the same line since we're using both variables, so this will update both simultaneously. Max of holding, not holding, minus price of I, minus fee. And at the end, we just get whatever the max is of, well, we get whatever we get if we're not holding, right? Because you could say, well, is it the max of not holding and holding? Well, if you're holding the stock, you had to pay money to hold it, so you definitely have more money if you're not holding on the stock on the last day. So not holding will always be greater than holding by the end of this problem. Oh, shit. Price is not defined. Price is... Oh, I did it again. How foolish can someone be, you know? Did I do it again? Guys, God. I just really don't want this to work. Leetcode subscribe, what? Okay. Come on, come on, come on, come on, come on. Oh, because I have to spend negative prices. I mean, I wrote that in my solution, but I didn't, you know. Right, because I lose prices, the first cost of the price, and then the fee when I'm holding it, right? Not holding. Here, okay. That's good enough for me. 3-line solution, pretty clean. Let's go over the runtime. So let's say that n equals the length of prices, right? So that's the number of days. For time, well, we just look at each day and we do a constant operation, where we do a constant operation to update both of these variables. So this is for each day, we do a constant operation. So for each n days, we do a constant operation. So that's big O of n. For space, well, we create these two variables, and then regardless of the number of days, we just keep updating these two variables, right? So regardless of what n is, if n is 10, if n is a million, if n is 100 billion, trillion, 1,000 quadrillion, we still only have these two variables. So it doesn't scale with anything. It's O of 1 or constant. All right, guys, that's it. It's a pretty cool problem, pretty difficult, but pretty fun if you think of it as a graph.